Okay, so if you had hopefully attended or watched the lecture about the math thing, and we stressed the fact that math is about extracting intrinsic features about objects. So differential geometry in particular is about extracting the intrinsic features of surfaces embedded in Euclidean space and generalizing this concept. What is really special about the surface in Euclidean space? What are the intrinsic features? So we're going to form a definition like we did here. What are the intrinsic features about the surface in Euclidean space? If it's smooth enough, at any point I can flatten it out. So here is the way we flatten it out. We just zoom and take this copy and flatten it out, right? And basically do our calculus here. So differential geometry is about generalizing, actually. We need to know the philosophy of this thing. So it's about generalization of surfaces. If you want to, look well educated, say hypersurfaces, because it's in hard dimensions. Surfaces in Euclidean space. Want to generalize this concept, okay? So we asked what was the unique about a surface in Euclidean space. We said the flattening ability, if it's smooth, and we did that. Okay, what else? What else? So if I have a surface like S2, for example, yes, I can flatten it out, each batch, and I can flatten it out. What else? In fact, we have the tangent plane, right? An intrinsic property to each surface in Euclidean space, smooth surface. We have a tangent plane, and if it's higher dimension, we call it tangent space. So for S2, for the sphere, at this point I have this tangent plane, at that point I have this tangent plane, and so and so. Right, at this point I have this tangent plane, this guy here, and so I have tangent plane at each point. And it's different from a point to another, so I have to stress the point in my definition. So that's okay, that's good. So in any surface, say if you have this surface defined by a function, f equal constant, in a higher dimension Euclidean space, I can easily define the tangent space at any point, say this point, P. How can you define the tangent space? Well, I have the normal to the surface very well defined. It's nabla F, right? And any vector V, any V that is perpendicular to nabla F must be in the tangent space. So this guy is perpendicular, this guy, so the form of all these guys form the tangent space, right? And this is easy to do if I live in a higher dimension Euclidean space. Note that this nabla F really lives in the higher dimension space, it's not on the manifold. And the dot product is defined because I'm living in a higher dimension space. So for any surface living in a higher dimension Euclidean space, I can easily define the tangent space. That's fine, the tangent plane. But the point here, what is the philosophy of differential geometry? Yes, the objective is to generalize surfaces in Euclidean space. But what's the philosophy? What are the goals? We need to do that without resorting to the fact that we live in a higher dimension space. We want to do it as if this is really our world. We don't see any other dimensions. We live here, we don't see outside. How can you define tangent plane while you're living here? Okay? Or tangent space. So how to define tangent space without resorting to embedding in higher dimension Euclidean space. Okay? So let's see, what have we have been doing so far? We defined the manifold, its flattening ability, we can map it into coordinates, we define differentiable functions, we define differentiable curves. So actually curves is a good way. Why? Because we can define the tangent space of P in M, tangent space of the manifold of your surface at some point. This is what we're gonna denote by TPM, and as you can see, we really stress the point in the definition because, as you can see, it's different from a point to another. This is the set of all velocities, right, of differentiable curves on M at P, or passing through P. So really in our picture, in Euclidean space, well, at this point, if I have a curve, the velocity vector here is tangent to the manifold, another velocity vector is tangent to the manifold, velocity vector of another curve, and so and so. So you collect all of these guys, you get the tangent space. This definition does not depend on the fact that we live in a high dimension space, right? Just get all your differential curves passing through the point, so get all their velocities at the point, they are just vectors. This is your tangent space, tangent plane, okay? Any question about that? So, like I said, the philosophy of differential geometry, generalization of surfaces without resorting to the fact that we live in a higher dimensional space, because even if we live, sometimes we can visualize like S2, some other times we cannot visualize. So this is why math is important in the sense we extract the intrinsic features and really don't care afterwards. In the sense, well, if any other object, whether it's really a surface or not, possesses the same features, which is the definition of a manifold, well, it will obey whatever we're going to get throughout the course. Doesn't matter if it's a surface or not, doesn't matter if it's a surface that we can visualize or we cannot visualize. So, like SO3, we cannot visualize in a convenient way, and I need it, but it's a manifold. I don't care really if it's a surface or not, or I can visualize it or not. It obeys the definition of a manifold, right? This represents the attitude. Anybody here, any point here, represents the attitude of a rigid body, which can be represented by a rotation matrix. Any point here is a matrix. Any point is a matrix, but I can very well define a curve, right? Passing through these guys, and I can define the velocity of that curve, right? And the set of all velocities of all these curves passing through a point, this is the tangent space of this ugly manifold at that point, okay? So this is the thing here. Let's have a little example. So gamma of t equals, it's a curve, so it takes a real number in an interval and gives you a point of the manifold. So this is like t over 2 square root 1 minus 5t squared over 4. This is on S2, okay? Gamma of 0 is, this substitute t of 0, so this is 0, 0, 1, right? So it's that thing, and if we get gamma prime, let's differentiate and substitute t equals 0. Obviously you get 1 half. Do this guy and substitute t equals 0, you get 0. So this is this guy. This is the north pole, B. And this is your vector. Obviously it lies in the tangent space, okay? So this is in TBS2, right? The tangent space of the sphere at the point B. But if you look at it, it's actually it's a vector in R3. We really gamma, the way I wrote gamma here, I wrote gamma in R3, relying on the fact that we live in a three-dimensional space. So I differentiated. If you want to do it without resorting to higher dimensional Euclidean space, when we really write gamma, we write gamma in coordinates, right? So let's pick some coordinates. Say, so in coordinates, for example, let's do the stereographic projection from some point. We need a stereographic projection where this point B is defined. We cannot do it from the North Pole, so do it from any other point. I'll do it from here. I'll do it from E. And we can project on any plane, maybe the vertical plane, from the North Pole to the South Pole. We can project on any other plane. I will do it on that plane. AA here, okay? So stereographic projection from E on AA. Follow the way we did it last time to get your phi. So phi takes a point on the manifold and gives you your coordinates. It's a two-dimensional manifold, so I would have here two things. Obviously, I'm projecting on the, if this is X, this is Y, this is Z, I'm projecting on the XZ plane, right? AA, I'm projecting on the XZ plane. You don't see it here. This is your point. Y, X, Z. So any point here, I'm projecting, like I said, on this guy. So any point on the sphere, I will project it on that green line. Okay?
Professor,
Yes.
you said that in the first part, while we differentiated, we resorted to that we live in a higher dimension space, and now we are doing it without resorting.
Yeah. So I'm doing it here in coordinates. Pick any set of coordinates. Your velocity vector passes through this point B, so you need any coordinate chart phi that covers this point. So I'm choosing this not nice way, which is I'm projecting here. So the coordinates of this point B actually will be over there. Okay.
My question was, why are we doing it at the first time like this? We were resorting to the higher dimension space.
This is in higher dimension space, right?
Why? I don't
What do
know
you mean why? Because yeah, that's a very good question. Thank you. So this is a vector in R3. I'm writing the vector in R3. So it's a tangent vector, right? Yeah, I know that it's tangent to one of the components may vanish, or it doesn't matter actually. One of the components may not vanish. But this will always be tangent to the sphere. This is how we constructed the curve. But this vector is in R3. This is a two-dimensional manifold, right? The tangent space is a two-dimensional plane. Any vector in that plane will have two components. If you live on the plane, if you don't see the higher dimensions.
Yes.
So I want to give you these two components, okay? So here we need to work in coordinates. Any coordinate chart. At the beginning, we agreed on that picture, right?
Yes.
So at any point, I can map, this is M, which is now the sphere, it's two-dimensional, I can map to a two-dimensional plane, I can work on that plane. So this is what I'm doing now.
Thanks.
So, what question here?
No.
Okay, so phi x, y, z, choose any one, I'll give you an easier one afterwards. Yes, Carlos?
So if I have a manifold in R4, for example, I need 4 coordinates for the tangent.
No, this is what I'm saying. So if you write in the ambient space, yes, you'll need 4 coordinates, but we don't want to do that. So the whole point of differential geometry, okay, we want to generalize the concept of surfaces, but at the same time, we don't want to resort to the fact that we live in high dimensional space. We will do all of our calculus on the manifold. If it's two-dimensional surface, we're going to do it all 2 dimensions, okay? So if you go and try to derive this stereographic projection like I did last time, nothing fancy at all, you will find the x and z, so this is like large x and large z. Now, you'll find this, I guess, if I remember correctly, this is 2x over 1 minus y, this is 2z over 1 minus y. Okay? So, very similar to what I did last time. So, this is the coordinate chart. So, when you write a curve, here is your curve, gamma. If you want to write it in coordinates here, how are you going to write it? How are you going to write gamma in these coordinates? It will be what? Phi composed with gamma, right? Okay? So let's do phi composed with gamma. This is the gamma that I just gave you. This is the gamma that I just gave you. T over 2 square root something. 1 minus t squared over 4. So let's do that. Phi composed with gamma. So it's phi of this guy. Right? So t over 2 and square root. So this is, now I'll give phi, will take 3 numbers and give me just 2 numbers, right? So 2x, 2 of the first, divided by 1 minus the second. 2 of the third, divided by 1 minus the second. Okay? Any questions about that? And now this is indeed your gamma. Yeah, we write it phi composed with gamma, but actually it's just my gamma written in coordinates. So this is gamma written in coordinates. Gamma in coordinates. So if you want to get gamma prime of 0, just do it, please. Differentiate and substitute t equals 0. You will get here, as you can see, 2. And this is a little bit complicated. You will get 1. This is in t bs2. And it's 2 dimensional. This is the vector that you get. Okay? And you can do it in any other coordinate map. Let's do it in an easier one. This is a little bit involved because the projection is a little bit involved. It's not very hard, but simpler one. Let's do in coordinates just xy projection. Why you're making it a big deal? Xy projection. So phi takes xy, z, project on x and y. That's it. So here, this point, we project down on the equator. Okay? We project everything on the equator.
Professor?
Yes.
Is gamma dash of 0, while we did it looking for the ambient space, is the same as gamma
That's
dash?
a very good question. We're going to talk about it in a minute. Okay. So xy projection, let's do it in xy projection. Again, gamma in coordinates. What's gamma in coordinates? It's phi composed with gamma. So this is phi of t over 2 square root 1 minus blah blah. And here we take what? Just the 2 coordinates t and t over 2. Now this is your gamma in coordinates. So what's gamma prime of 0? It's 1.5.